As I was working with materials for this unit on mental models that we're doing right now, I began thinking about how mental models have changed over the years in terms of how we design instruction. Now, of course, I'm particularly interested in designing instruction on computers, and it really seems to me that over the years, our mental models have evolved in ways that have significant impact on instructional designers. And I think that instructional designers really have to understand mental models and how they work. And so I thought I would share with you some of what I've learned over 25 or 30 years of working with computers in education, and how we use them to design instruction, and how that has evolved over the years. Okay, first, a definition to make things clear. We're going to be talking about two things here: mental models and conceptual models, and you need to know the difference between the two. Mental models are what we're talking about, cognitive structures in the brain. So mental models exist in the end user, the receiver of the instruction, the user of the product. That's what's going on in their heads. Those are the things that are also called sometimes schemata or schema. We studied that in this chapter. So these are models that exist inside of your mind that basically tell us how things work. They are based on our perceptions and our experiences, and basically they give us clues when we see something new, something we haven't seen before. Our mental models gives us a way to start to think about how to use that item. Now, mental models are not universal. Your mental models are different than my mental models, and mental models are incomplete. So obviously none of us ever have the facts, but the human brain is constructive. And so when we have incomplete facts, our brain puts it together to construct a model that makes sense. And that's why our mental models can differ quite a bit from each other. We've all had different past experiences, and we all have different intuitive perceptions. Okay? But we all have these mental models, and good product design, good design, has to recognize these mental models. Okay, these mental models shape our actions and behavior and influence what people pay attention to in a complicated situation. Now, when you think about that, that's very important for education. What people are paying attention to really influences what they remember, and of course, remembering is a very important thing. Mental models also define how people approach and solve problems. Again, very important from the standpoint of education. Now, a conceptual model is actually the implementation of the object or instruction that you are making. Now, notice that I'm using the terms object and instruction kind of simultaneously. We're going to be talking about design here, and it doesn't really matter what you're designing in. Design principles are the same. When you are designing something, you are going to build something, you're constructing something. And when you start constructing that, you have an idea, you have a conceptual model of how that thing will work. Now, when the user receives that model, again, whether it's instruction or an object of some sort, they have to figure out how it works. The better your conceptual model fits their mental model, the easier they will find it to use. Okay, the relationship between the mental model and the conceptual model is very important. And the reason is that one of the major ways that people learn is through a process called isomorphism. That is, by mapping ideas, what they're trying to learn with what they already know. It's putting things into a one-to-one correspondence. So if you have a good isomorphism between the conceptual model of the instruction you've designed and the user's mental models, okay, that means that they're going to be able to map what your expectations are against what their expectations are, and things will go very smoothly. At least that's the idea. Okay? Now, that means that to the highest degree possible, when you design a product or instruction, you should use a conceptual model that fits the user's mental model to the greatest degree that you can. Now, there are limitations. Okay? The problem is that if the design of the product does not match the image that people have in their minds, their mental image of how that product should work, then it's pretty likely that that product is not only going to be difficult to learn, but it's not going to be easy to use. Okay? Now, of course, you can train users' mental models, and in the early days of computer education, of course, there was a big emphasis on training for teachers, training for people using computers, because people didn't really understand computers. So the computers really were not powerful enough to be adjusted to what users wanted. So, the way to overcome that is you train. You teach the user how to use the material. Now, clearly, the better your models align, the better your conceptual model aligns with the user's mental model, the less training would be needed. Okay? Now, obviously, if you want to just extend the logic of that one more degree, what that means is a perfectly designed object would need no training. Now, I just want to mention here that several years ago, I ran across a really interesting book called The Design of Everyday Things. And this is one of the things that the author talks about. In the world, you'll see many things that really are not well designed and therefore really confuse you and are not easy to use. And I'll give you some examples. So what happens when you come up with a conceptual model that does not match users' mental models? The result can be catastrophic. And I'll give you an example that I remember during my study. And that was calculators. Now, we all have a mental model for a calculator. We kind of know, if I were to ask you to close your eyes and picture a calculator, you've got a mental model. And so when you come across a calculator, you have assumptions about how to use it. You got a pretty good idea how to use it. Well, in 1977, HP came out with a thing called the RPN calculator. Now, you have to remember, 1977, the state-of-the-art technology was much weaker than it is now. What HP wanted to do was to design a calculator that could do advanced scientific and statistical calculations with very limited capacity. Okay, so they came out with this computer, and as you can see, it looks sort of like a computer. It doesn't really blow up your mental image in a sense. It looks like what you would expect. The problem was it didn't work the way that you expected it to. Now, how do you expect a calculator to work, you might ask? Well, I'll give you the simplest example. If you wanted to add 2 and 2, the keys that you would press and the order that you would press them in, you'd press the 2 key, then the plus key, then the 2 key, and then the equal key, and you'd get the answer. That's how people expect calculators to work. But in order to make their calculator more advanced with limited capability, they made the user learn the way that computers store information, particularly real numbers. And that is in what is called a stack. I'm not going to go into stack arithmetic right now. If you want to Google it, it's semi-interesting, I suppose. But anyway, in order to facilitate that, they used a different kind of notation for the arithmetic called reverse Polish notation. That is not an ethnic slur, folks. That's what it is actually called. And it's called that to distinguish it from Polish notation, which is what you just saw. We don't call it that, of course, but in mathematical circles, I guess it might be called that. The interesting thing is the way that you put the information in was to facilitate how the computer stores information rather than how we expect it to be stored. And so you would actually have to press this. Now notice that, by the way, this is called outfix notation. And what that means is that the sign of the operation, in this case a plus sign, is outside of the 2 numbers that it's operating on. And that looks a little odd. The net result, by the way, is that the HP RPN calculator was not that successful a product. It was only used by very nerdy engineers and people like that, and never found acceptance. And the reason is, of course, that it did not work the way people expected it to. Now, when you're designing a conceptual model, you are making assumptions about how people do things, and that's what your conceptual model is going to be based on. What you're going to do is you're going to attempt to integrate what you know or think you know about the user's mental models, and we'll talk about how you might do that a little bit later, with the conceptual model of the product. The goal here is to design a product, again, or instruction, that requires no training. The product tells us how to use it, okay? And the things on the product that tell us how to use it are called affordances. This is an important term in the design world, and it's one that I would like you to understand, so we're going to talk a little bit about affordances. Okay, so let's talk a little bit about what affordances are. Again, affordances are the features of objects or instruction that provide us clues on how to use the device or to operate the device. Let's take a really simple example, a chair. Now, you might say, well, gee, that's a pretty simple device. And yes, it is. Have you ever noticed that no chairs come with instructions? I mean, you know, you buy a chair, you don't have to be trained how to use it. Why is that? Okay, the reason is that we have a mental model of a chair. And we know how a chair works, and we know what the affordances of a chair are. What we would say in the design world is chairs afford sitting. A chair affords sitting. Sitting is an affordance of a chair. Okay, now here's another chair that I found on the internet, and I would suggest to you that it's a poorly designed chair. If you looked at it, you might not even know what it is. It doesn't match our mental model. The affordances are not obvious. Now, by the way, this chair was not designed particularly to be a great chair. It was designed as a work of art. And so I'm not really speaking about it as a work of art. I'm talking about it as a design for a chair. Not a good one. The affordances are not obvious. It does not tell us how to use it. Now, ever since I read that book, The Design of Everyday Things, I've become a little bit of a nut on this, and the things that I notice all over the place that just drive me crazy in terms of badly designed everyday objects. And one is a door, okay? Now, a well-designed door would have the affordances, the features that would tell you how to use the object. For example, here, we see that the affordances here are handles. Handles afford pulling. So when you look at that door and you want to figure out how to operate it, I would suggest to you that the word pull, which is training, right? You're training the person how to use it, is redundant. You don't really need to say pull because the affordance suggests pulling. Handles suggest pulling. A better designed door is this. Notice that the only affordances are steel panels for pushing. The only thing you can do with this door is pushing. Any instructions would be ridiculous. And so this is a really well-designed door. Now, here's one that I find a little odd. The affordance is for pulling. It's a handle. And yet the instructions are pushing, to push. To me, this is cognitive dissonance. When I find things like this in the real world, it makes me laugh because I think, wow, that's really stupid. Okay? And of course, the really stupid one, you know, says to pull, but there's no affordance for pulling. You can't pull that door, and yet that's what it tells you to do. Okay, so these are, again, I want you to understand what the idea of affordances are, and then we can talk about how affordances have changed with the mental images over the past 30 years. One of the main challenges of designers is to overcome the limits of the technology. And again, I've been working with computers for 25 years, so I've really seen how mental models have evolved in terms of computers. I mean, think back to those early computers. I don't know if you remember, but, you know, output was restricted to, in some cases, monitors that had text only. Now, the first two computers that we had here at FAU, when I was a graduate student back in the 80s, we had Apple IIs and TRS-80 Model 1s, the so-called Trash 80. The TRS-80 only did text. There was no color, there were no graphics, just simply text. I mean, you know, some people had green screen monitors, but they were just text too. They were a little fancier and a little bit more real computer-like, but text. Now, the Apple, on the other hand, had graphic monitors. And that, by the way, is probably the reason why Apple became the dominant computer in education. Because those of us that were in education and interested in computers recognized the need for graphics, animation, and color way before the, quote, real computer people did. Okay. Back in those early days, though, the graphic monitor had limited colors. The Apple, I believe, you were limited to 16 colors. Can you imagine that? Only 16 colors could be displayed on that monitor. And of course, the resolution was incredibly limited, very kind of blurry and not at all like high def like we have now. And of course, for input, we only had two things. We had the keyboard, which I talked about a little bit, and the joystick. And that came along a little bit later, in fact. I can remember in the early 80s, we were setting up a lab here at FAU. I was a graduate assistant. And the brand new Atari computer had come out, the Atari 800. And it was really neat because it had great graphics. And of course, again, those of us in educational technology were interested in color and graphics and so on and so forth. So we had a little money, and so we ordered a couple of Atari 800 computers for our lab. Now, by the way, the fact that they were the first computer that were really good for games had absolutely nothing to do with it, I assure you. We wanted them to experiment with them for educational reasons. Well, nevertheless, we put in the order for the two computers, and we put in an order for two joysticks. The order for the joysticks was rejected by purchasing because they came back and said, we know what you're up to. You're buying that joystick to play games, and we don't use university money to play games. So they wouldn't approve it. The next week, we resubmitted the order and asked for two analog input devices. No problem. We got them without question. Now, early software, of course, had to accommodate the technology. Same problem as with the HP. You know, you want to do advanced things, but you got limited technology. How do you do it? And I'm going to give you some examples. Some early games and how gaming has evolved, because I think gaming and education are tied in together in terms of immersion and lots of other things I don't want to talk about right now. How application software has evolved over the years, and how our mental model of application software has evolved. And, of course, computer-assisted instruction, which is something that should be of interest to us. When I first started teaching computers to students, to teachers, and so on and so forth, my first class was to a group of senior citizens. It was kind of interesting because most people did not have a mental model of computers and how they worked and what they could do. I mean, the whole notion that, you know, input, process, output, that sort of thing, they just didn't have a mental model for it. And it was very difficult to get them to learn to use computers. Now, of course, computers had limited capacity and there wasn't really much they could do, but to even tap what they could do, you had to develop some kind of mental model about how it worked. And the key here is that you had to adjust your mental model. Because of the limited capacity of computers, we did not have the ability to develop robust conceptual models that would match your existing mental models. Okay? Little thought in those days was given to how the user interfaces with the machine. You would write your program, and you might write a user interface later and so that users might be able to use it, but you didn't really think about it too much. I can remember students coming in and looking at the computer and just not figuring out what it did, how it worked. It didn't have a lot of affordances. I mean, heck, it wasn't easy to find the on-off switch. It was hidden in the back. Okay? And students didn't even know that you need to look for an on-off switch. That's how simplistic their mental models were. Again, luckily, that's evolved over the years. As I mentioned, the first microcomputers had very simple affordances, a very simple keyboard, very limited monitors. Okay, and let's take a little bit better look at the keyboard. Now, this is a keyboard of an early microcomputer, and obviously somebody designed this. Somebody had a conceptual model, and of course their conceptual model was of a typewriter. Okay, now people, of course, have a mental model for typewriter, and so when you look at this, you have an idea how to use the product, correct? The affordances are very simple. Keys, like a regular typewriter, and, you know, a couple of extra keys, seemingly that don't belong there. Because we didn't really, you know, again, we didn't really have a mental model of a computer. So, again, very few affordances, and the design was intentionally based on mental model that people already had in an attempt to make it easier to use, with limited success. The opening screen of an early IBM PC. You know, when you start a computer now, you see menus, you see things to point at, you see places to click. Here's what you used to see on the old IBM PC, the C prompt. You had to know what the computer's model was. The computer did not have any idea of what you did and how you did things. That made early microcomputers, as I'm sure many of you remember, incredibly difficult to use. What made them difficult to use? The conceptual model did not closely match the mental model. Couldn't. We didn't have the capacity to. When I first started teaching computers in education, I used a lot of mental models to help students try to understand what computers were. Again, they didn't really, in those days, have a mental model of what a computer is. So I can say, okay, let's take a look at a word processor. Okay. Your mental image, your mental model here is a typewriter. Now you have a mental model for a typewriter, so now you have some idea of what a word processor is. And this was by doing this, it helped students develop mental models that got them involved in something to help them figure out how to use a word processor. Well, you know, what do you do with a typewriter? You know, you type in information, you correct it, you go, you know, that sort of thing. That's what you do with a word processor. Database, well, you guys know what a file cabinet is. You have a mental image of a file cabinet. You even know what to do with a file cabinet. You file things. You put things in, you retrieve things, you move things around. That mental image will help you understand what a database is. The toughest one, of course, was a spreadsheet, because the mental model of a spreadsheet is a ledger, and most of us have never really dealt with ledgers. I mean, most of us have used typewriters and file cabinets, but many of us have not really kept books per se. But depending on who you were, one of these three things could have been the main thing to hook you into the world of computers and change your mental model in terms of what you thought computers could do for you. And so, you know, the first word processors, you know, based on the mental model of a typewriter, very simplistic. Helpful, because since you know what a typewriter is and we're telling you this is like a typewriter, it does make the product easier to use. Keep in mind, however, that on the negative side of that is it limits how you think about the product. So if you think of a word processor as a typewriter, that's helpful in terms of the affordances that tell you what it does and how it does things. But if you think of it as a typewriter, you're missing a whole lot. And over the years, the evolution of the mental model of the typewriter has evolved tremendously, from a simple way of entering and editing text to the advanced functions that we have now. And so we're going to take a look at how that evolved over the years. Again, I'm going to give you examples from application software, games, and CAI. In general, the really successful applications were the ones that were best able to use the affordances available at the time to give users the best user experience. And again, at the early days, things were very limited. The first really great word processor, the one used by everybody, the one that pretty much was universal, was called WordStar. And as you can see, it has a very simple interface. This is a green screen monitor. And it looks pretty cryptic. You'd had to probably study it for a while to figure out exactly what to do. Some of the commands seem a little confusing. For example, you can see there's a command to open a non-document. Okay, what's that? Anyway, this was a very popular word processor, but even in the early days, they recognized the need for conceptual models built on people's mental models. And the first, really, one of the first of those was the concept of a menu. Okay, we all have a mental model of what a menu is. Menu is a thing that gives you a series of choices to make, and you choose from that menu. Those are the only choices you have. You really can't get anything else, okay? So that's what a menu is. So we take that mental model of a menu and we say, okay, we know people know how to use menus, and so we're going to design a program that is based on a conceptual model of selecting things from a menu. And that really makes a lot of sense when you think about it. Just to show you how cryptic these early programs could be and how much they lacked affordances, okay? Now when you open a program, you should be able to look at the screen and get some idea of what to do. Check this out. This was the opening screen that you were presented in a program called DBase 2, obviously a database program, and you're given no help at all, no clue as to what to do. The only thing you're given is the kind of infamous to us old-timers dot prompt. See it way down there? Okay, I'll highlight it for you here. But that was it. You had to know what to do. You were not given any help at all. Again, I think games are tied in with education in terms of exploring the leading edge of graphics and animation and stuff like that. So I talk about games also, and the early games were really terrible. You know, no graphics. Again, if you can imagine, no graphics, no pictures, okay? The only way to get input was the keyboard. The only way to interact with the computer was the keyboard. So you would type something in, the computer would print something out. That was it, okay? Now, in the very early days, the output went to a printer, but I'm not that old. The output would go to the monitor, but basically that's all it was text. Here's an early one, Zork 1. Okay, and you can see, you know, you're west of the house, you're standing in an open field, there is a small mailbox here, and you would type in open mailbox, and it would come back and say you've opened the mailbox, and there's a, you know, and that would be the interactivity, okay? And so you had to use your imagination. Now some people say that was better. Some people like that. I don't know if you guys like The Big Bang Theory. It's one of my favorite shows because it's about weird college professors. And one of the things Sheldon says, he's playing the game of Zork, his comment on it was, it uses the world's greatest graphics processor, the mind. You know, early computer-assisted instruction obviously suffered from the same limitations, you know, talk about the same computers. Few affordances, little memory, not much processing. And so early computer-assisted instruction, again, text-based. Here's an early one that's actually still around, of course, in a much evolved form. Very similar to the adventure game we saw on the last slide. All text. You see very crude graphics, but it's really hard to actually call those graphics, okay? So again, you would type something in and it would come back and so on and so forth, and that's pretty much how it worked. The idea of Oregon Trail, by the way, was to tap in to your mental model of exploring and how one would explore. And so they developed this conceptual model of, you know, we're preparing to go on a expedition on the Oregon Trail as a way to involve you in the educational experience. So very clear attempt to develop a conceptual model to change the user's mental models. Pretty cool. Right around 1990, 1991, IBM got into the PC business. Before that, they decided that PCs weren't really what any people needed. What people needed were their big, gigantic computers that they sold. Well, go figure. Notice that I'm calling this the IBM PC. That's sort of an inside joke with old computer people, of which I am one. IBM is kind of famous or infamous for coming up with some pretty good products with some pretty pedestrian names. For example, many years ago, they came up with a programming language, and they named that programming language APL. APL stood for a programming language. When they came out with their IBM, personal computer, the name of the computer was the PC. It was called the IBM PC. So some of us used to call it the IBM PC, because IBM PC was actually the name, and it was a PC. Yeah, you get it. Anyway, I said it was an inside joke. I didn't say it was a funny inside joke. What was the big push with the second generation? Well, first of all, it legitimized microcomputers in business. It changed people's mental image of why you would have a microcomputer in the world of business. Okay, now you wouldn't have, I mean, very few people wanted to have an Apple. A big businessman doesn't want an Apple on his desk. But now he could have an IBM on his desk, his own IBM computer. And it just changed the way the business world looked at personal computers. It legitimized them. Okay, and again, now the mental image was, if you want to get ahead, you got to learn how to use this. Totally different. Much more power. Now, I can tell you that the Apple computer, its processing speed was 1 kilohertz. The IBM was 4.77, nearly 5 times more powerful. Paltry by today's standards, but it could do more things. It could allow you to design more affordances that would allow your products to be more congruent with what the users were expecting, because now we had more power. We had better graphics. We had all that sort of thing. And, of course, we had affordances. And this was a huge breakthrough, the IBM keyboard. This is still what your keyboards look like, folks, unless you're an Apple guy. Yes, the old mental model is still there, right? We still have the QWERTY keyboard, and it still inputs text that way. But IBM recognized the need for additional ways to communicate with the computer. Okay, and so it came up with these programmable function keys that would allow programmers to tie specific operations to programming keys, and then the user could just simply, select the function key and do things that they would not have been able to do before. Okay, so it also had, other keys that were useful that expanded our mental model of what computers could do. And this was a very important development, and one that rocked the world, particularly the world of word processing, because WordStar just didn't get it. When the IBM PC came out, the people that were WordStar did not change their conceptual image. That left the door wide open for a company like WordPerfect. Very soon after the introduction of the IBM PC, WordPerfect unseated WordStar as the dominant word processor. Why? Well, the folks at WordPerfect understood the new affordances made possible by the PC keyboard. And just that understanding of the shift of mental image from the old keyboard to the new key, they got it, WordStar didn't get it. Okay, and so they developed a conceptual model based around the new affordances, which allowed users to work in a way more congruent with how they thought things should work. Okay, and they introduced the keyboard template, which was very clever, very simple. What it did was, it was just a little thing that fit over your function keys. And rather, for example, in WordStar, okay, if you wanted to make text bold, you had to memorize a sequence of keystrokes. Control K, Control B, Control B. It was, I don't remember. It was a long time ago. Okay, but now with the keyboard template, if you notice on the right-hand side, halfway down, there's a thing that says bold. So if you want to make something bold, you just push the bold button. I remember when this happened, folks. I got to tell you, it blew my mind. It was so superior to the old word processors that we were using, just by this very simple developing of an affordance that made it possible to do things that were really more the way I expected them to happen. Obviously, this reduces the need for training. You don't have to teach people complicated keystrokes. It makes it much easier. No training? No, you got to still have training. We still had training, but it was now easier to train people. Another shift in mental models made by WordPerfect, by the way, and the one that blew my mind more than anything else and totally changed the way I thought about word processing was WordPerfect was the first word processor where you could open up 2 documents at the same time. Now, that doesn't seem like much these days. You can open up 30 or 40 if you want. But in those days, if you wanted to work on a second document, you would have to close the document you were working on, open the new document, and go from there. You could only have one. And it just changed the way you could think about moving things from one document to another, cutting and pasting between documents. It just changed the way you thought about word processing. Changed my entire mental model. Now, the second generation games, of course, also took advantage of the advanced processing power, graphics, and affordances. But as an example here, I want to give you an example of something that wasn't really essentially, or at least primarily, a computer game. This was an arcade game. And I just think it's very interesting. And it's the most successful game in the history of games. And it was Pac-Man. I'm sure you guys remember Pac-Man. They're still around. The reason I wanted to mention it is that it was this game that really first attracted me to the world of computers in education. That may sound weird, but let me explain. It wasn't that I was addicted to playing it. I really wasn't. I only played it a few times. What I found fascinating was that adolescents would sit in an arcade for hours putting quarters into the machine, one after another, to play this game. And this fascinated me for a couple of reasons. First of all, I thought, what if we could get them to be this engaged in an educational experience? Wow, wouldn't that be special? We still really haven't done that, but you know, that was a really important thing. The other thing that was of interest to me, and I remind you that my degree is in psychology. We just studied behaviorism. From a behaviorist point of view, this is the weirdest damn thing in the world, okay? In behaviorism, an organism exhibits a behavior to get a reward. When you're playing Pac-Man, you give a reward to engage in a behavior. I mean, that would blow any behaviorist's mind. You know, playing Pac-Man is a behavior, is behavior. It's doing something. And money is a reward. So, you know, the kid is punishing himself or giving a reward to the machine for providing it with the opportunity to engage in a preferred activity. Now, there is some evidence of this in the world of psychology. There's a thing called the Premack principle, but I'm not going to really talk about that right now. You can look it up if you want. But basically, it's a theory that says, that was kind of the justification for things like, you can give the kids as a reward free time on a Friday afternoon. The idea being the opportunity to engage in a preferred activity is a reward. You know, the idea that behavior could be a reward, again, mind-blowing to behaviorists. Anyway, why was this the most successful game in the world? I mean, it amazed me. Well, look at the affordance. This was the control for the entire game. To play Pac-Man required absolutely no training. You had a simple affordance that only moved 4 ways, and the little guy on the screen moved the 4 ways with it. Zero training, total engagement from the beginning, no downtime learning how to use it. You can have fun right from the beginning. Again, I would love to figure out how to design computer-assisted instruction that uses this principle. You know, the idea that something could be very easy to learn and very easy to get people engaged in, but kept getting a little harder and a little harder and a little harder, and kept raising the bar and kept engaging the student more and more and more. By the way, I still haven't designed this program, but I'm still thinking about it. You know, at this time, second generation CAI was, you know, pretty much like an arcade games, using the same arcade game technology as before. Here was a very famous one called Math Blasters, and you can see it uses the keyboard, and what you do is it tells you to type in the missing number, and when you do that, it blows something up, you know, and it's supposed to be very motivational. And again, what they were trying to do is exactly what I was trying to do, which is to design something that would be engaging and involving right from the beginning and get harder and harder. This didn't really do it, by the way. It wasn't that engaging and it wasn't that good. In 1985, it all changes. Macintosh is introduced, and within a year or so, Microsoft introduces Windows. What was the big change here, folks? And it really fits into the theme of this presentation. Before the Macintosh, every person who designed a product for the computer designed their own conceptual model. That is, their own model of how the program would operate, and some did it very successfully, some did not do it as successfully, some matched people's mental models pretty well, some didn't. But it didn't, one thing that didn't matter, and that is learning the mental model for one program in no way helped you with another program. So learning WordPerfect did not help you with Lotus 1-2-3 one bit. The mental models were completely different. The conceptual models were completely different. What Macintosh did was they moved the conceptual model up from the software level to the operating system level. They said, okay, here's a conceptual model of how computers work. And we spent a lot of time making it work like we think your mental model works. And once you learn how this mental model works, it doesn't matter what you're doing. It doesn't matter if you're doing word processing or database or whatever. Yeah, you know, those programs may have their own little, you know, idiosyncrasies that you had to learn. But in terms of selecting things using a mouse, those are the same. And so the conceptual model changes now, okay, and becomes much more robust. And now when you design a new product, if you wanted to get the official Windows okay or be an official Macintosh product, you have to design your conceptual model in their way. In some ways, it maybe takes freedom from you. But what it does is it allows the user, and you do this all the time, and I do it now, buy a new piece of software, install it, and immediately know how to use it. What a change from the old days. Okay? And so this was the first attempt to really design a conceptual model for a whole system based on users' mental models. Now, of course, those mental models had evolved over the years, but and you know, by 1985, most users had some ideas of how computers worked, but the whole notion of a graphical interface of, you know, so the idea is, you know, one of the things you want to do on a computer is to choose things, right? You got to pick things, like the old menu, okay? Well, how do people in the real world pick things? Well, they pick things by pointing at them. That's your mental model, okay? And so point and click and so on and so forth became our mental model. We all know how to point and click. We know how to drag and drop. We know how to do the things that, and by the way, it doesn't matter if you're Mac or PC. You can go from one to the other. They work the same way. Why? They're based on the same conceptual model, pretty much. New affordances, you know, you have the mouse, obviously, very graphical computers. Drop-down menus, buttons, sidebars, radio buttons, all of the things that we take absolute for granted in today's computers is really new. Like I say, we take a new piece of software now, we don't even bother, we don't even care what computer it's on. You know, Mac, PC, Linux, no problem. They're all the same. Okay, the conceptual model has been kind of solidified, and people's mental models have kind of solidified. So back in the old days where I used to spend 3 sessions of an introductory computer course in how to operate the computer, now we spend 10 minutes, if that, because people already have mental models of how computers work. Pretty awesome how things have changed in not a very long amount of time. And so when we see a piece of software, again, whatever, do you care what browser this is? Do you care what computer it's on? Do you care if it's, no. Why? Because the affordances have become standardized, okay? We know what drop-down menus are. We know that menus afford selecting from choices. We know how they're categorized, okay? We know that icons afford actions. Icons are to be pressed, okay? We know that text boxes afford entering text. So when the computer needs information from you, it's going to give you a text box. Doesn't matter what the program is. I happen to be using a browser here, but these are standard throughout Windows, throughout the Macintosh. Buttons, you know what to do with a button. Buttons are always actions, right? So now, again, because of the evolution of our mental maps and our mental concepts, computers have become easier and easier to use. And computer-assisted instruction, of course, has become easier and easier to develop. And now, of course, we have all other kinds of technology that have developed new conceptual models. On the left, you see a Samsung S3. On the right, you see an iPhone. If you can tell me the difference, I had to really look at them for a second. If you borrow your friend's iPhone and you're a Samsung guy, it ain't going to matter. Why? The affordances are the same. Now, one thing that does matter, by the way, if you're developing instruction is it kind of complicates things in a way. If you develop a piece of instruction that you want students to be able to see on their cell phone or iPad, that takes a little advanced work. Now, by the way, a really cheap and easy way to do it is the way I've done this presentation. Narrated PowerPoint, saved as an MP4, upload to YouTube, and people can view it on anything, iPhone, iPad, Google, whatever, okay? I'm just sharing that with you for no additional charge. I hope you enjoyed the presentation. Okay, in conclusion, I'd like to make a few comments. And first of all, let's assume that you believe me that an understanding of the user's mental model is necessary for good design. You might wonder, how do I do it? Well, there's several methods. I won't go into it in great detail here, but some of the things you can do is, and again, these are some of the things that instructional designers do, a task analysis, behavioral observations, checklists, that sort of thing, interviews, and of course, focus groups. These are all ways that instructional designers use to develop an understanding of a user's mental model so that they can develop instruction that is easy to use and effective and efficient. Secondly, the challenge is really to design a conceptual model that designs the user model, and one of the main areas here is the interface design. The interface of your product should be what the user expects. We've seen over the years several examples of companies coming out with really innovative interfaces that had a lot of trouble because people couldn't really fit their mental model to it. One that I recall was Authorware. I had a lot of difficulty with Authorware because their conceptual model was a stage and theater and actors. Okay, well, that was not one that I was familiar with, and so I found it difficult to use. Whereas Flash used a timeline. That made more sense to me. So when you're designing something, you really want to tap into what the user already knows. Also, as you're developing the model, you want to do a lot of evaluation along the way. So you don't want to completely develop your entire product and then test it. That you might find out it's not working and it's not a good thing. But you want to do a lot of testing during the development of the product. Okay, and obviously after the product is completed, some validation testing. Everything that you see here on the screen right now, These are all tasks that are undertaken by instructional designers and all things that you will probably run into at some other point in this course.